When we introduced column compression capacity the other day, we considered strictly the idea of a vertical load being imposed on the column. However, most columns actually fell as a combination of both compression and some sort of bending. And this relationship is called interaction. And so today what we want to do is take the idea of compression capacity, or column capacity rather, and figure out how to calculate it for this combined compression and bending effects that occur. Now, first thing I want to do is introduce how this might occur. So let's look at how bending might be introduced into a column. So we're going to draw two different diagrams here. These are the two most common ways that it happens. The first one, we'll just draw a column member, compression member. This could be a stud in an exterior stud wall, something like that. And we know that there's compression capacity that comes down, and of course this has to be resisted along the bottom. But what happens when the wind blows along the side of the column, or the wall rather, causes the column to want to actually bend now. Now you've got compression capacity, and you've got that compression capacity pushing downward on the column, but you've also got this net effect pushing inward on the column, trying to buckle it. And so this causes the column to want to bend. The second case that is quite common is if we have some sort of a load that is not straight down the center of the column. And this often occurs if we have some sort of a beam hanger, something where the beam coming in is acting out here, not down the center of the column. And what we end up with is this distance between the load acting vertically and the center of the column. And you know that if you've got a force and some sort of a distance, we create a moment. The fancy way of saying this offset bending moment is a term we call eccentricity, or they just use a little lowercase letter e to describe this. Again, you can see because the load is not coming down the center of the column, we get some sort of a bending moment that is provided on this column. And in both cases here, you've got a column with a compression or a vertical load coming down and some sort of a bending moment that is being created on the column. So in this case, we would want to work with the interaction equation because these columns have both compression and bending acting on them. All right, the theoretical form of this equation exists by plotting what the bending moment capacity versus the compression capacity would be. So along the bottom, we'll put the bending moment capacity. Along the y-axis, we'll put the compression capacity. And interestingly enough, if you were to think about this kind of in a theoretical sense, if the compression capacity were completely at its maximum value, we couldn't have any bending moment capacity. So bending in that case would be equal to 0. And we'll use P for point load, 0 just to represent that that's the maximum value that can have. We'll label that max point load capacity acting up along this axis. Similarly, there's a point where this column can handle as much bending as is possible, but without any compression. And so in this case, we'll use M for moment, and this would represent the maximum moment capacity. Maximum moment capacity. P for point load capacity, M for moment capacity. And again, both of these occur when the opposite effect is 0. In theory, these could be connected with a straight line. And if you had a certain bending moment that was acting, n for just some nominal value that exists, if you had some sort of a bending moment that was acting on this particular column, well, then what that would do is it would say, I've got some sort of compression capacity that is lower than maximum that then will meet the failure line, and as long as I stay beneath those two values, I won't fail. The theoretical form of this equation then would be the ratio of the actual point load capacity compared to the maximum value, and then we'd also have the ratio of the actual bending value compared to the maximum bending value. And so long as that remained less than or equal to 100% of the capacity, that blue line represents that capacity, then we won't have a column failure. Now usually we don't deal with things in terms of actual point load and bending moment. Typically we convert everything to stress. And so the theoretical stress form of this equation simply becomes the compressive stress actual relative to the allowable, the bending stress relative to the allowable, and so long as that again is less than 100%, then this particular column won't fail. So this, just to go through those one more time, we've got actual compressive stress, allowable compressive stress, actual bending stress, allowable bending stress. And as long as those two ratios added together maintain and remain less than a value of 100% or 1.0, then this particular column should be okay. Now, what I want you to note is this is the theoretical form of the equation. This is just the concept of looking at compression capacity versus bending moment capacity. But every material will behave just a little bit different. So when we talk about the actual interaction equation, we have to look at a material-specific equation. In your textbook, on page 491, it shows the interaction equation for timber. And it follows this basic form of compressive stress ratios versus bending stress ratios. But there's just a handful of specific details that are specific to timber. So another weird thing about your textbook is the equation is actually in there incorrectly. I've posted the correct form on Learning Suite if you need to see it there, but I'm also going to put it right here in this particular video. So when we look at the compression capacity, we take the actual compression capacity, compare it to the allowable compression capacity. Note that I put the apostrophe or the hyphen on there because that accounts for the different adjustments that we've been speaking about. For some reason, this equation then squares that term, but generally speaking, we're talking about the compression ratio there. Then what we do is we compare that to the bending capacity. Note it's little bending capacity, actual bending stress. I think your textbooks uses a symbol X in there as well. That's simply to notate the weakest axis, but we'll leave that off. Then they compare that to the allowable bending stress. And then there's one more embedded parameter here, 1 minus the compressive stress over the actual compressive stress. And what this particular term does is accounts for Euler's buckling right there. So in a nutshell, we've got the ratio of actual compressive stress to the allowable. We've got the ratio of actual bending stress to the allowable. A couple other adjustments in there for the sake of making this timber specific. It's the way that the timber empirically behaves. And then we just need to check and make sure that this relationship is all less than or equal to 1. This is how we run the interaction equation. This is the better part of your homework. There's 4 different terms that you then have to come up with when you're calculating this in your homework. So long as you calculate the compressive stress actual, compressive stress allowable, bending stress actual, bending stress allowable, and then note over here, this is simply the actual compressive stress that we're dealing with, and so there's no new terms in there. What I like to do is calculate these 4 values separately, just plug them into the equation, and go ahead and solve the interaction equation. Make sure that we have sufficient capacity in the column that accounts for compression and bending. I've got another video that will walk you through the example. There's an example PDF and an example video, and I recommend that you utilize that to actually now work your interaction equation homework problems.